Okay, cool. Now it is. So I'm going to start by talking about chapter 7 stuff, because I know that's where you guys said that you were kind of like the most worried about.
Mm-hmm.
How do I put it in a text box? All right, so Dr. Dowdy isn't going to make it too difficult for you guys. And if you guys know probably like this stuff that I'm about to tell you, it'll be super easy breezy. So we have S, and then the N is like teeny, so I'm going to put it like that. So we have like SN2. SN2 reactions happen in one step. Their order of reactivity is that they like methyl, and then they'll do primary, and then they will do secondary, and they won't really do tertiary, but I'll include it here just to show you guys that that would be like the last option, even though it like won't happen.
Wait, are you writing on the screen?
Yeah, writing.
Oh, you guys like can't see it as I write it.
Oh, there we go.
Oh, there we
Yeah,
go.
there we go.
Okay, there we go. Sorry, I'm like typing it. I guess you guys can't see. I'll start fixing that. Okay, so then we have methyl. The rate equation looks like K. That's an alkane substrate, nucleophile.
What do you mean by
And
methyl?
So methyl means like, it would look like this. Like let's say that we have like a BR here, and then this is our leaving group, then it's only connected to a CH3 like that.
Oh, okay.
So that wouldn't even be primary, that would just be like a methyl, if that makes sense. So yes, that is what I'm talking about there. And then over here, the rate equation looks like that. So that's called second order. And then over here, you're gonna have a backside attack, and that flips configuration. I'm actually gonna make this entire page for SN2, and then we can do another one for SN1. So you have a backside attack that flips the configuration. Stronger the nucleophile, the better. These are kind of some things that I would just like maybe write on the side for the exam, like as you go, like on your scrap piece of paper, if it comes up. So better leaving group. And so you have a faster reaction. And then over here, so we have polar aprotic solvents are what is going to be.
Wait, when you say stronger the nucleophile, the better leaving group, you said?
So the nucleophile is different than the leaving group. You guys will get into, this will be relevant once you get into E2 reactions. It's actually nice that he isn't grouping the E2 reactions with with like SN1 and SN2 reactions, just because that's when nucleophiles, like the strength of the nucleophile, and if it's a base or a strong base, is relevant. But just for right now, just kind of don't worry about that point. When we do the final review, that will be
I had
relevant.
a question because like the second to last bullet point, it says stronger the NU, the better, but then like it doesn't say anything after the better.
Yeah, so like if it was a weaker nucleophile, then it wouldn't be as good as like a stronger, like the better
Oh,
for the
okay.
reaction.
Okay,
Yeah,
thank you.
yeah, no
How
problem.
do we identify if it's the nucleophile is stronger or not?
So nucleophiles we know will donate electrons or accept electrons.
Donate.
Yeah, so they're going to donate electrons. So something like oxygen isn't as good as the nucleophile as something as like Chlorine. Actually, I guess chlorine would, yeah, chlorine can donate electrons. It just like wouldn't want to donate electrons because unless it's like gonna benefit itself to like give itself that octet.
So would like a metal like sodium Na would be a strong, if it was, would be like a strong nucleophile?
Sodium Na.
If it was like NaOH, yeah.
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 Okay.
But there's periodic trends in chapter 7 you can look at that
Yeah.
tell you whether it's a stronger or weaker nucleophile.
So I feel like this is really messy. I wish I did it on my iPad. Would you guys prefer if I did it side by side? I'm actually gonna clear this. I'm so sorry.
Can you put it back for 1 second?
And I'm gonna make it. Did you ask me to bring it back? I'm gonna write it so that it's more organized so that you guys can actually see it, because I feel like the table actually does make a difference. So like over here we have SN2, and then we're gonna have our SN1 reaction. So in SN2, it happens in 1 step. Over here we have the order of reactivity is methyl, and then primary, and then secondary. And then over here, the rate is K, substrate, nucleophile.
The substrate, the
Over here we have a factor. Sorry, what did you say?
is the substrate the reactant?
Yeah, the substrate is the reactant.
Oh.
Flip the stereochemistry. Oh, sorry. It's going to be different than that. So then we have a stronger nucleophile.
What does it say under backside attack?
Flip configuration.
Flip
Sorry, I'll try and like make my handwriting a little nicer.
No, you're
And by the leading group after the reaction, and then we have our polar aprotic solvents. And so a way that you can kind of remember these polar aprotic solvents, like something that's going to be the same between all of them, is that they do not form hydrogen bonds. H and P do not hydrogen bonds. Sorry, what did you say?
Is that Cu3CN?
CH3CN, yeah. So that'll look like this. It could also look like this, like we saw on the worksheet today. And the carbon can have a minus sign on it. And then over here for SN1 reactions, we have that happens in 2 steps. The order of reactivity is tertiary, then secondary, and then kind of maybe not really primary. Rate is dependent only on the substrate. And then we have first order kinetics. And over here you have a trigonal planar, couple of cations, intermediate. And we would have favored by weaker nucleophiles. Again, it's not really going to matter because if you know those solvents that the solvents that you have, you'll be able to like look at the question and be like, oh, for sure, I know if that's SN1 or SN2. You have isomerization of products. That means you're going to get a mix of R and S. Better leading group. Faster reaction. And then over here for our polar protic solvents, we have ethanol. Just gonna have our OH on the end. We have NH3, which is ammonia. We have our acetic acid. We can have methanol like this. We can have just water, or we can have formic acid, which pretty much just means like it has like a carboxylic acid. And then over here, that is what our graph would look like, our energy diagram. And then that would look like just one. So, yep, that is pretty much what this would look like. So if you guys want to go ahead and take a screenshot of that, then we can get into the practice problems.
I have a question. So
Yeah, what's up?
the polar aprotic solvents, they're going to be strong because they're going to be connected with metals only. Is that what it is? That they're stronger with bonded to metals?
I wouldn't really worry about if it's what it's bonded to. I would kind of just know what the solvents are and then know that it's going to react with like SN1 or SN2, if that makes sense.
What
Just,
would
like,
you
know it.
recommend? Sorry. What would
Okay,
you
good.
recommend looking at first when you see a reaction? Would you say like look at what type of carbon it is, if it's like 3rd degree or 2nd degree, or looking at the solvent?
I would personally look at 1st degree, 2nd degree, and then I would look at the solvent, and then I would kind of just like make sure that I know if it's going to be SN1 or SN2 for that reaction. But personally, I do like to look at tertiary, secondary, or primary first.
Yeah, because secondary, it could be either. So like I guess when it's 3rd degree, you could just say that it's going to be SN1, but when it's 2nd degree, you have to look at other things, like if it's aprotic or protic solvent.
Yeah.
Yeah, exactly. But do look at the substrate just to like make sure, or sorry, look at the solvent just to make sure.
Okay.
Like, just check. Okay. So I guess we can get into questions if you guys are ready. Okay. Cool. So first question, let's go ahead and rank in order of the, okay, I'm gonna like mess up the spelling, but like rank in order of triangle Freelance system. So when we see this, we know that we're going to put the highest priority first. And this is the system that we use when we are putting in R and S configurations. So let's say that our first option 1 is CHO, 2 is CH2OH, 3 is OCH3, and then 4 is COOH. So the first thing that I would like to do for this is actually write out what it looks like. And so this first one is going to look like this. So this is an aldehyde. Second one looks like this. But just keep in mind where we're bonding it to. Over here, this one actually does look like this. So we'd have C double bond. Oh, so this is like a ketone, but we're actually being bonded to this. So kind of just like know where you're actually starting at. So it looks like this actually. And then you have your carbon with your 3 hydrogens on it. And then the last one here looks like this. So this is a carboxylic acid. And we know in this one, we have, since this one is bonded to an oxygen, we automatically know that that one is going to win. So we have 3 comes first. And then after that, we are going to have 4, since this is double bonded to an oxygen. And it also has an OH on it, so that has the most amount of oxygens. And we know that like oxygen is really up there because based on the periodic table, it would be able to like donate it's just like better than carbon, I guess, for size. And then after this, we would have the 1 because it is double bonded to the oxygen like this. So then we have 1, and lastly we have 2. So the way that you can kind of think about it is that this looks like this. So we have like COOH because each bond counts as the atom being there twice. So in this one, we have like O, C, this one we have C, O, and then in this one we have COOOH. Does that make sense? The H's are kind of irrelevant though, so you honestly don't even have to put them in there.
I'm sorry if you already explained, but why does 3 come before 4?
What happened?
I think it's frozen.
Oh.
I thought it was just me.
No.
But were you asking why did the third one come before the last one, the fourth one?
Yeah, because I was confused because number 4 had 2 oxygens,
Hmm.
so I was just confused why 3 came before 4.
I think it's because
The oxygen came first. Yeah, the oxygen came first. So
Oh, okay.
it's kind of like you can look at it per like letter. So all of them have besides the oxygen, besides the third one's the only one with the oxygen in front, and the others have carbons. So oxygen is higher priority than the carbons.
Did your power go out?
Yeah, my power actually did go, but the show must go on.
oh my god.
I don't want to like have to keep this session running like too long, especially because it's already like ending at 11. So I'm just gonna keep going. Is that fine with you guys?
He's
Yeah.
on numbering.
Thank you.
Completely confused.
Yeah, no problem. Hopefully they figure it out. 1 second. Okay, perfect. So I'm trying to join on my iPod. Becky, no. He's asking me to watch a movie. The session is loading on my iPad still. Okay. Let's see. Okay, cool. So did you guys have any questions on the last one where it was like oxygen came first, so that one?
Explain the numbering again and like how to get there because I'm completely lost.
So if you guys like look at the periodic table, remember how like even I feel like that question kind of like a little bit complicated, but say like we have a molecule that looks like this, where this is carbon, this is bromine, this is oxygen, and then this is another carbon.
Mm-hmm.
Oh, great. light came back on. Fantastic.
Mhm.
So I guess the power is back on. That's super nice. I feel like I live in a third world country. Okay, so let me try and connect to the internet because that's probably gonna be faster than my hotspot. Okay, the internet is not back on yet, so we're just gonna keep going on with this. So, just like due to size, we know that bromine would be 1, and then oxygen would be 2, carbon would be 3. So it's kind of just like the same thing. And even if we have like carbon bonded to oxygen, this carbon directly bonded to the oxygen would be better than this carbon that's bonded to the oxygen like that. Does that make sense?
Basically, like ordering it like from increasing atomic number almost for these two.
Yeah.
Yeah,
For
that's
this one,
priority.
it's atomic number.
Okay.
It's kind of the same thing that we're doing for R and S.
Yeah. So we will do practice questions for RNS. Oh, how do I clear this? We will do practice questions for RNS. So, yes, we will do that. But over here, let's just get into the next question so we don't waste too much time. It says draw an energy diagram for an exothermic SN1 reaction. So obviously there would be options like A, B, C, and D. But we know that with an exothermic, we're gonna have like a negative delta G happening. Delta G doesn't change whether you add a catalyst or not, but pretty much what would happen is that like over here, energy is increasing. Over here, we have energy increasing. So at the end, our products are going to be down here so that we know that we're releasing energy. And because we know that it's SN1, this one over here is telling you how many things the rate depends on. So if we were to break down SN1, we have this is substitution, this is nucleophile, and then 1 is this how many things the rate depends on. So we know that rate is dependent on just the substrate, but kind of like you can kind of think like just SN1 reactions, you're going to have 2 steps. So that means that we're going to have 2 pumps like that. And then that's kind of like an example of what an SN1 exothermic SN1 reaction would look like. Cool.
When you just threw, isn't that SN2? Oh no, that's SN1. That's SN1. Never mind.
That is SN1. Yeah, you're good. Don't worry. So then next question, let's say that we have how many of
label the activation energy and the delta H for this one?
you won't have to.
Okay.
Yeah. So these kinds of questions where it's like how many of the molecules shown are chiral, I always get like super like tripped up about just because I'm like, well, like one of these answers here is definitely correct, but they're all pretty similar. Do this.
I can't hear you that well. You're frozen again.
Maybe she's connecting her Wi-Fi instead.
Oh, there we go. Sort of.
Is that better?
Yes, now that's better. Yeah.
You kind of sound like a piano. Do I still sound like a piano?
It got like a little better.
Yeah.
Wait, did you
I'm
even raise
really
the last
sorry.
problem that you just had about how many of the molecules shown are chiral?
I'm trying to go to the other. Okay, so for some reason the other one is like not allowing me to click on it, so I'm just gonna click. I'm just gonna draw it again then, I guess. Oh, there we go. Now it showed up. Perfect. Okay, so over here, the next molecule looks like this. Other molecule looks like this. Cl, and the next molecule will look like this. So how many of the molecules shown are chiral? So we know that having a chiral center isn't enough. So over here, but that doesn't look like it's the case here anyway, so it doesn't really matter. But over here, we're gonna have this center here is not chiral because this has two of the same things connected to it. So this one is not chiral. This one here has a Br. Okay, that looks pretty good. And then there's a methyl over there. So this is a different one. This is a different one. There's a hydrogen over here. So that means that yes, this one is chiral. Next one, okay, it's kind of like the same thing as the one that we just saw. So this one right here is a chiral center. So that one is good. Perfect. And then over here, this one is connected to two hydrogens, so that's not going to work. This one here has two methyls connected to it, so that one is not chiral. So this one is not a chiral molecule. So that means that within these four, we have two chiral compounds. Any questions about this one?
So if it has a chiral center, it is a chiral compound?
So not necessarily, because it can be like a meso compound, and we know that meso compounds aren't considered to be chiral.
Is that
because
symmetry?
Yeah, because they have that plane of symmetry, and we know that chiral compounds will be able to, if you like put plain polarized light on them, then it will flip the configuration, but with chiral compounds, it won't. So that's why meso compounds are just not considered chiral. Does that make sense, kind of?
Yeah.
I feel like I just said the word chiral so many times, but the show will go on. So over here. Okay, so next question is going to be, what is the order of rates from fastest to slowest? So the reaction looks like this.
What is the order of what?
Fastest to slowest. So then this is where we're going to see the strength of the nucleophile, and I feel like this will help explain the strength of the nucleophile. So over here.
Your voice is kind of like breaking up a little bit.
Yeah, I'm sorry, guys. The internet just like isn't the best here. There isn't really like anything I can do about it. I'm really sorry, you guys.
It's okay.
But I'm just gonna keep going, and hopefully next time it's a little bit better.
Oh, whoever's behind you, we said hi. They waved.
Yeah, he's my brother. He's being extremely annoying right now. So over here we have an OH. We have a CH3 with an O that's charged. So it's like really ready to give away electrons, if that's a hint for anybody. And then over here we have the NH2. And so if we were to, something that kind of like helps me is actually drawing it out, like with the electrons on there. So then this one looks like this. And then this one looks like this. And then there's a lone pair of electrons. And so from fastest to slowest. So over here, we can see that it is replacing it. So obviously this is going to be a substitution reaction. Strong nucleophiles are electron donors. Oxygen is the best because it has the most lone pairs. And then NH2 is going to be second best, but OH is the worst. And this is also a pKa kind of question. So based on like acidity, so we know that bases are electron donors, so you can kind of just keep that in mind. But if we were to just rate this based on the information that we have, then we see that this one is going to be the best. So then if we're going to rate it, it would be 2, 3, and then 1. Because you see that this one can like readily donate it. And then OH is kind of like bad at a lot of things in organic chemistry. It's a bad leaving group, and it really isn't going to want to give away any of its electrons because then it's going to form a plus sign on it. So if this oxygen over here were to form another bond, then it would look like, I guess it wouldn't look like that, it would look like this, and then it would have a plus sign on it, and that's just like not a good look for the carbon. It's better for the nitrogen to have a plus sign on it. So like let's say that that one formed a bond because nitrogen is less electronegative than the oxygen. Does that make sense?
So is this ranking in terms of strength of the nucleophile?
Yeah, so this is fastest to slowest.
Fastest, oh.
Wait, so what is the equation or reaction that's above that?
This is just a bromine being replaced by a nucleophile. So we wouldn't know if it's, actually, I guess we would know that this is an SN1 reaction, but it's not really relevant here.
Oh,
Because all
okay.
of these are able to form hydrogen bonds, so then we know that it's SN1. Cool.
Wait, I thought SN1 has 2 steps.
It does have 2 steps, so I guess like if we wanted to like actually draw what the mechanism would look like, it would look like this. Bromine leaves. We have a charge on this carbon, and then we would have our nucleophile come in like this and attack that carbon with a plus sign. So we have a nucleophilic attack, and then at the end of it, we have nucleophile.
Okay.
Fun, right?
Like possibly do more questions with the arrows.
Yeah.
Yeah, we'll definitely do more. That's kind of like what I have more towards the end. These are kind of just like talking questions now, but I have arrow questions and like 5 questions. Yeah. So are you guys ready for the next question? This is going to be a bond dissociation energy question.
Oh, yay.
Okay, awesome. So over here we have rank the following indicated bonds. The following indicated bonds in order of bond dissociation. I do think he's going to ask a question like this, so just be wary of this trend. So we know that if we have something like this, this is just the trend really quick. Iodine, this is increasing larger molecule. And so with something like fluorine, so just know like larger the molecule, easier it is to break the bond. So you need less energy. So this is saying in order of, I didn't even write it, but it's supposed to say increasing, or sorry, decreasing. So with something like fluorine, another way that you can think about it, fluorine is the most electronegative atom. anyways, so if fluorine bonds to something like hydrogen, so we have like HF, it's going to be like super duper hard to break that bond due to the fact that fluorine is definitely going to like steal that one electron from the hydrogen and run with it. So now these are our options. We have Cr bonded to C, Cl3, F bonded to C, Cl3, I bonded to C, Cl3, and then Cl bonded to C, Cl3.
Wait, so we're ranking those? The
Yeah,
ones
so
you-
we are ranking these.
Okay.
And so the answer for this one is going to be 2, 4, 1, and 3. So this is like most energy to least since we are decreasing. As we just mentioned, fluorine is going to need the most energy, and then Cl, so that's 4, and then Br, so that's 1, and then iodine, which is 3. Cool.
So is it based off of which is smaller, or is it based off of which is more electronegative?
So it's both, but size is like the trend, and then if you're trying to remember, and then just remembering that fluorine is the most electronegative atom will help you remember the trend.
Wait, so it's like the higher the atomic number, I guess, the higher the dissociation energy? Or is the opposite?
Just
No,
think
it's
of it
based
like
off the size. So like as you go down the periodic table, it gets bigger. So it's
Oh,
gonna
okay.
dissociate easier.
Think of it like this. So we know that our protons are in the center, and they're what are holding on to our electrons on the outside, right?
Mm-hmm.
So if you have something like this, and it's increasing in size, we're adding an extra orbital each time we go up. It's easier to take electrons from something like iodine than it is to take electrons from something like fluorine. Because if you take this and you have your hydrogen like that, that's not going to want to break. Or if you have your CCl3 for this example,
Mm-hmm.
that's not going to want to break. Whereas if you take something like this with iodine, where you have CCl3, it's like soup. You don't really need too much energy to like throw it in there and just break the bond once it forms.
Okay.
Does that make sense?
Yeah.
Does that picture kind of help?
Yes.
And you guys will have a periodic table, so you won't have to like memorize this. Just remember the size of them all. Thinking about how fluorine is the most electronegative atom is like a little bit too advanced, you know? So yes, a couple more questions and then we'll get into drawing. So over here, rank the following leaving groups from rank the leaving group from worst to best. To best. So let's say that we have something like NH2. I feel like Dr. Dowdy hasn't mentioned that what is it called? That OH is like a super bad leaving group to you guys yet. But I remember when I took Orgo, he mentioned it like every single lecture. I mean, it is. So like he has the right to, you know what I mean? We have 1, 2, 3, and 4. So like I've mentioned like 3,000 times, OH is a really bad leaving group, but okay, I guess it's like OH isn't the worst leaving group. Technically CH3 is the worst leaving group because methyl is like, you can think of it as like its own person. So, and it's also the least electronegative. So it's the worst leaving group because once it it's not like happy on its own. Like if you had a CH3 like this on its own in the wild, then it's not going to be happy. So least electronegative, it's going to be the worst leaving group. So I guess me saying OH is a really bad leaving group is a little bit like misleading. So CH3 is the worst because it's not happy on its own. And then after that, oh my gosh, NH2, also really bad leaving group. Technically all of these except for water are bad leaving groups. So this one is more electronegative negative than C. So it's not like as big as a baby if it were by itself, but it's still less electronegative than oxygen. So then after that, it's going to be 1, and then like I said, 3, and then 2. So water is like super happy on its own. It's actually like a pretty decent leaving group. If you had a molecule, like once you guys get to Orgo 2, you'll see that there are molecules, there are reactions where you actually make OH water so that it can be a good leaving group. So I guess this is an electronegativity kind of trend. So the less electronegative it is, then the worse a leaving group it is. The less electronegative it is, the worse a leaving group it is. Cool.
Would it be when you make a relationship between leaving group and basicity, would it be like where the stronger the leaving group, worse the base, or would it be vice versa?
So bases are good at donating electrons. So oxygen is the best electron donator out of all of these. So I guess it would be the stronger the base, the better the leaving group it is.
Yes, thank you.
I just use electronegativity in this one to like determine which is the best and like worst leaving group. I'm confused.
Yeah, so on the periodic table, you have this. That would be increasing, or like worst to best leaving group.
Mm.
Cool. And then obviously water is a better leaving group than OH because OH is not happy on its own, like it's like all charged, whereas oxygen is like completely chilling. Happy molecule on its own. Cool.
Mm-hmm.
Have you guys gone over electrostatic potential maps on this exam or the last exam?
Mm-hmm.
That was the last exam.
I think it was the last one, but I don't think he even touched on it that much.
Yeah.
Because I don't remember it at all.
So next question then. I'm going to type this one up if it works, because sometimes it's not going to work. That's fine. We're just going to write it. So compound 1 has a specific rotation of 8.5 degrees. That's positive. What is the specific rotation of compound 2?
Will he
say
give
that
us the
kind one
formula
is
on the
this.
exam?
You're not going to need the formula. This is kind of like one of those questions. I don't know if you guys see those TikToks where it's like, oh, it's this question on the ACT, then the answer is going to be 0. I don't know, my For You page is built like that because I'm addicted to school. This is kind of like one of those questions where if he gives you something like this, the answer is just going to be the opposite.
Oh.
That would be the answer. Unless he keeps it the same. But he wouldn't do that. But I'm like, 75% sure. I don't want to say 100% sure, but I'm pretty sure that if he asks you a question like this, it's just going to be the opposite. Because over here, we flip the configuration from that to that. So specific rotation changes. Just flips it.
If he did not flip it, what would it be the same?
If he didn't flip it, it wouldn't be a question. Like, how would he ask that? If compound 1 has a specific rotation of positive 8.5, what is the specific rotation of compound 1?
Okay, yeah. I get you.
You just wouldn't be able to ask a question like that. So, if you just ask a question, that's most likely how it's going to be asked. Cool.
Yeah.
Any questions on that? Okay, I'm going to ask you guys to tell me about this graph that I just wrote. Is this endothermic or exothermic?
Endothermic.
Endothermic. Is it SN1 or is it SN2?
SN1.
And it's going to be SN1, exactly, because it's happening in 2 steps. Where is the rate determining step? Is the rate determining step at 1 or 2?
1.
1.
Yep, it's at 1, because that's where the highest, what is it called, activation energy is. Cool.
Wait, what was it
Any
again?
questions?
Endothermic?
Endothermic, SN1, rate determining step is at 1.
I have a question. So is it if the
What's
higher
up?
the activation energy, the slower the reaction is? Or
So what? No, it's not slower. I guess so. Yeah.
Yeah, I think it's
The
slow when
activation
it's higher.
energy.
okay. Because if you put like 2 arrows for like 1 and 2, 1 would be slower.
Yeah,
Mhm.
and 2
Because-
faster.
Yeah, so like if you were to add an enzyme into this reaction, and we kind of cover that in exam 1, but if you added an enzyme, it would lower the activation energy of this. So it would it would look like this instead. So like reactants and products would be at the same place. Okay, I didn't keep them in the same place, but let's just like pretend they were in the same place. You're requiring less energy.
Okay, thank you.
Sorry, you guys. My brother decided it would be a good idea to unplug my computer charger. Okay, so we're gonna continue moving on. Do you guys have siblings? Little siblings specifically?
Mm-mm.
Wow.
Yes.
Yeah.
Yeah, they're annoying.
It'd be like that. In the middle of my session too. Did you unplug my iPad charger? Okay, perfect. Let's move on. So over here, next question we have, ooh, this is a fun one. This is a very tricky question. So let's just like try and focus our minds for this one. Chapter 7 stuff. So let's say, what happens in the following reaction if the concentration of the reagents is doubled
Do those
and
mean concentration?
yeah, that's what the brackets mean. And the concentration of the reactants stays the same.
Does it double?
Does it stay the same?
So I actually have to write out the equation at first.
Oh.
So we're gonna have a chlorine with a CH3OH turning into this. Okay, so Ibrahim is saying that it's going to stay the same. Ibrahim, do you want to explain to us why it's staying the same? The answer is a similar question in the homework. So.
Yeah, true. Yeah.
Would it be because it's an SN1 and SN1 reactions don't really need, don't have the reagent in the equation, just the substrate?
Yeah, awesome, you guys. So over here, how can you guys tell that this is an SN1 reaction?
Because it's 3'
Nucleophile.
tertiary.
Yeah.
Is that it?
Yeah, because SN2 can't have that, right?
And also, so yeah, that's a marker. And then also over here, our solvent, we can see that is obviously an OH. So OH is able to form hydrogen bonds. Polar aprotic solvents are not allowed to form hydrogen bonds. So over here we have our solvent and our tertiary. So over here we have rate is going to equal K equals substrate. And so substrate is the same thing as the reactant. So this would be K times this. And if you're making that stay the same, nothing else really matters. So then the answer here is going to be that the reaction rate is unaffected. Is everybody good with that?
Okay.
Yeah.
So is that how it would show, like the K and then the concentration of that?
That's how rate would be shown, which I know is like so weird that there's like a molecule in there, because in Chem 2 it's like a number. But yeah, that's how the rate would be written in the answer choice if that were the question being asked. So you guys want to do another bond dissociation question? You guys want to look at what the reaction would look like here?
Yeah.
Yeah.
Okay, I'm going to erase this bit down here. And the actual mechanism for this is this. Chlorine, like we mentioned before, is a great leaving group. So it's going to like leave on its own. Just like, honestly, I'm sick of you guys. I'm out of here. Then we have an electrophile. So this is our electrophile here. And this is where we have our carbocation intermediate. And then we would have a nice little chlorine over here floating. Let me not put plus chlorine. Let's put it away. And the chlorine is minus like that. And then over here we would have our OH. And it would kind of just like dissociate from the H3, which I know I mentioned like wouldn't happen before. Technically in this, the methyl would leave because it would get electrons from someplace else. So actually, it's gonna be over there. But pretty much what would happen is that this is gonna come over there. This is gonna be our nucleophile. And then our final product is going to look like this.
Could we do a transition state thing? Do we need to know that?
Transition. What's the transition state? Do you have a particular question you want to go over? Because that was honestly like the biggest gist of the exam questions that I got to go over with you guys just now. So if you guys have questions right now, we can take a little break to answer those and then get back into the ones that I have.
Yeah, let me see what it was like in the book. I think I sent it in the group chat today. It was in. Dang, I
Are
didn't.
you in the group that's called Organic Chemist? Oh, you didn't send it in the group chat?
Yeah, that's where I sent it. It was in the organic chemistry group chat. It's like that last picture I sent, and it like has it asks you to like draw the transition state. It's like 4 messages up. It's like right there.
Yeah.
Is this all chapter 7? Or is there still more to it?
This is mixed, like chapter 7, 5, and 6.
And could we do from the like the problems in the back of the book? Do you have those?
I don't have the book with me. So, but if you guys have questions that you wanted to go over, we could definitely go over them.
Yeah.
Could you
I
go
do have-
over?
Naming.
I want
Yes.
to go over 6.49 in the practice problems. I can
Okay.
like send a picture to you.
If you want to text me and say drawing group me, I'm going to do this one transition state question, and then after that, that is, what kind of equation is that? Is that an elimination equation? Why is it doing that? Oh,
Can we do naming too?
Yeah, we can do naming for sure. But something to mention for SN1 is that SN1 can sometimes do rearrangement. So like something like this can happen. Oh, let's say that this has like a plus sign over there and you want that. This methyl can like literally shift the entire thing so that this way you have now a, okay, actually you wouldn't want to do that. You would want to do, I'm trying to think of like how it looks like, because it would want to just, actually this wouldn't happen. A question he might even ask is like, which of the following will not happen? No, not happen. This, however, this could happen, I think. There's an example in your PowerPoint that I know is really, it does a much better job than how I'm trying to think of it in my head, because it's a difficult concept to understand, but just know that the carbocation is best off being like tertiary, but that also depends. I'll look at your PowerPoint and I'll explain it to you guys better, but I definitely would go over that concept, because he can ask a question like, which of the following reactions would not happen? And it would be the one where the carbocation is going from being something like tertiary to primary. It wouldn't want to do that. It always wants to be more substituted so that it can be more stable on its own, because it is good to have, like, we know that transition states are like super unstable, but like it's awesome if we can make them like kind of stable. Anyway, so let's do an IUPAC naming question. How about that?
Yeah.
Cool. Awesome. So I'll give you guys a second to answer this. What is the name for this compound?
We're putting the S and R in there too, right?
Yeah, SNR. And I'll give you guys like 2 minutes to answer that, and then we can.
I'm sorry, did you already go over the transition state one that I was asking about? Oh, okay.
Okay, does anybody have an answer for this question?
Yes.
Okay, what's your answer?
2s, 3s, 2,3 dibromo, 4 methylpentane.
You guys agree?
I got like almost exactly the same, but I put hexane.
Carly says that she doesn't agree. Carly, what did you get? I feel like Dr. Dowdy.
I got 2s, 3r dash bromo, 4 methylpentane, but I don't know if that's right. I'm kind of confused.
Just bromo? Dibromo or just bromo?
It'd be dibromo, right?
Mm-hmm. Perfect. So the answer here, and we'll explain that in a second, but is 2s, 3r, 2,3 dibromo, 4 methyl pentane, like that. Cool.
Wait, why is it 3R? Because doesn't it like flip? Or I mean, why is it?
So we're gonna run it through really quick so we can understand it. Over here we have a Br. Technically over here there's some hydrogen on dash, which is like so not cool. Bromine is 1. Over here, you can think about how there's a bromine over here. This carbon is going to be 2, then this is going to be 3, and that's going to be 4. If we do that, then we get an R. But we see that our 1 configuration is on a dash, and that's not cool. So we're going to make it an S. So we have 2S. And then after that, we have something that looks like this. Other substituents do technically matter here. So then we have bromine like that. And then this is going to be 1 for this carbon over here. Then this carbon is going to be 2. Then this one is going to be 3. And then obviously
Why is
we
it
have
2
our,
and then 3?
because this one is connected to a methyl and a bromine. And the bromine is better than the methyl.
Okay.
Okay.
And they're both tertiary carbons. Like they're both carbons that are connected to, I guess they're actually not both tertiary carbons. One of them is primary and one of them is secondary. One of them is tertiary and one of them is secondary. But one of them has a better group on it. So it's kind of like we're comparing this group, like as well. Like that, it just has a higher priority group on it. So that one is 2, this one is 3.
Okay.
And then if we were to do that, then over here we get R. Cool.
Yeah.
Yep, exactly. So like this section here has a higher priority group, or it's like heavier than this section here. this section. Oops, again. Oops, again. Then this section. Does that make sense, you guys?
Yeah.
Awesome, awesome. So then, obviously, methyl on 4. And that's our answer.
I have a question. So
Okay.
I actually numbered it differently. I went 1 through 5 straight across.
Oh, like this, you move the like this.
Yes.
Same thing.
Okay.
Yeah. This is not a chiral carbon. It not that that has anything to do with it, but it's just the same thing either way. Methyl is on 4. Now if this were like this, then it would matter, but it's not. Same
Okay.
ending. So we're just gonna. I did it like that strategically, just to like show you guys how there's different ways to number it, but yeah, same thing. Next question, compare these two compounds. So we're gonna have this. And I remember going into this exam and I feel like I missed like half of these types of questions because I hadn't gone over these properly. But you guys can learn from my mistakes. And over here we have a Cl. So what are these?
Are they enantiomers?
Enantiomers.
Enantiomers, yeah.
So I have a, okay, wait a minute. I actually put in the wrong equation over here, or wrong molecule. So I guess we can calculate if they're going to be enantiomers or not. So enantiomers are non-superposable mirror images of each other, and yeah, they are enantiomers because we flipped the whatever configuration it was before. RS to bromine is 1, so I guess the first one is. Let me play as, so it's actually R. Yeah, so we're moving from an R configuration to an S configuration, and everything else is staying the same, so they are enantiomers. Great job, you guys. So then next question here, we have this, so keeping with
still
that
comparing?
same. Sorry, what?
Are we still comparing, like whether they're enantiomers or diastereomers and that?
Yeah, that's what we're still doing now. I have like a couple of examples for this, and I do want to get like an example of each one. Okay, what are these?
Stereomers.
Final answer?
Diastereomers.
They're
So we know that
split.
diastereomers are just when we have change in configuration of one of the stereogenic centers. So we know that to have diastereomers, we need to have 2 stereogenic centers, which we do have here, but something else changed in this molecule. Do you guys know?
They switch places, Cl and Br.
Yeah. Is it
Cl and then Br. Yeah, so they are constitutional isomers. Awesome. Because we have difference in the connectivity.
Yeah, okay.
Constitutional isomers. Next question. Oh, my bad. Okay, what are these?
Anatomy.
So we have a vote for enantiomers. I have another vote for enantiomers. One more person can answer.
Meso compounds or enantiomer? I always mix those up. Whether it's like a meso compound or if it's an enantiomer.
Meso is just if it has a center, but it's symmetrical or something like that. I think that's different.
So these are enantiomers. This is another way to draw enantiomers. We know that, I guess like maybe I should have made like one of these CO. Let's make one of these CO. Yeah, a mesocompound does need at least 2 stereogenic centers, which we do technically have here. So I put in the CL so that it's no longer symmetrical.
Oh, okay.
Yeah, there you go. I changed the question on you guys. So now they are enantiomers. But before that, I guess they weren't even. I mean, technically with a triangle, it depends on where you want to draw your. No, they were symmetrical before that. So, yes. Okay.
So what would
These are
the first
enantiomers.
one have been?
The first one would have been, I guess, also enantiomers. They wouldn't be. Yeah, they would still be enantiomers.
Oh.
They just wouldn't be chiral compounds in the first one. Cool. Which enantiomers doesn't have to do with chirality. Oh, well.
I have a question. So,
Yes.
can they be mesocompounds if they're not like both on the same plane, like how it was before? Does it matter if they're on the same plane or not?
So the thing about mesocompounds is that they have stereogenic centers, but they are
Achiral, I believe.
yeah, so they're achiral, so they don't transfer plane polarized light, but they still have their RNS configuration. So yeah, in order for mesocompounds to be mesocompounds, that's what's changing the two different mesocompounds. So like, let's say that we have something that looks like this. Oh. Okay. Do you guys have an example of a mesocompound? I guess, is this a mesocompound?
Oh, there's like a cyclohexane with 2 BRs attached would be like if they're symmetrical.
Okay. Yeah, because what actually makes the let's do a plane of symmetry here. So they're superimposable on each other. So then a different mesocompound would look like this. I think the thing about mesocompounds is that they look like enantiomers, but they're just not. Is that cool for everybody?
So would that one not? Oh no, it wouldn't be. Okay.
Yeah. So they wouldn't be enantiomers because they have a plane of symmetry. Is everybody good with that?
So those you just
No,
drew, those are meso compounds?
Yeah, so these are mesocompounds. But I feel like for mesocompounds, if he does ask you, I would know the definition. So they are superimposable mirror images or something like that. Look at the definition for mesocompounds and know it word for word. Know it maybe from the homework, because you guys have that definition homework that's in there. And that can probably be helpful, to be honest. So this one is going to be a tricky one. So I will let you guys think about this for a couple of seconds. So we're still going to compare these two, because I honestly do think that he might have a couple of these questions on the exam. Like if he asks it, it might be in multiple parts. Or else that's how he used to ask questions like this my exam. So like, but that was in person, so it kind of just depends. What do you guys think? What are you guys thinking? Walk me through your thought process.
I was thinking it was Dissociation,
Yeah.
Yeah,
Thinking
that's
the
what I
same.
thought too.
but I always get
Dice.
confused when it's just one thing like that.
You guys. Enantiomers.
Yeah.
I thought it'd
And
be
I have to look in-
enantiomers.
Enantiomers. Oh, this is.
Is it identical?
Oh, they're the same thing, aren't
It's
they?
identical, right?
Yeah, there you guys go. They are identical compounds because an enantiomer for this can look like this. So like, let's look at the enantiomers for this one. This is an enantiomer for this one. Like this, if I were just to switch the configuration, or this is also an enantiomer for this one. If I were to draw the mirror image of it. But if you draw the mirror image and you flip the configuration, then they are identical compounds.
Can you repeat?
Cool. If you flip the configuration and you draw the mirror image of a compound, then it will be its identical compound. Another way you can do it is, honestly, for all of these, I would look at the RNS configuration while doing these. So like, this is our chiral compound. I guess nitrogen would be best here. So like 1, and this would be the second best, and then I guess that, and then there's like a hydrogen just like randomly there. So we have over here an R, and then for this one we have 1, 2, 3, like that, and then we have an S. No problem with that because 1 is, I guess, nope, yeah, exactly. So because technically over here we have a hydrogen on a wedge, then we flip the configuration from S to R. If the configuration stays the same and you flip it, then the molecule is the same. Cool. An example of or let's do our last example here, and then I'll ask you guys what it is. So I'll say that we have Br here, we have OH on a dash, Br here, OH on a wedge. What is this? You know, you guys have been waiting for this one. I've been waiting for this one.
Diastereomer.
Yeah.
And these are diastereomers. So yeah, diastereomers for this one. So next question. Have you guys gone over addition reactions at all? Definition of addition reactions? I feel like you did. I recall him
Yeah, we
going over
have.
it in lecture.
Yeah.
Okay, wait.
Isn't it breaking a pi bond?
So what kind of reaction is this? And what kind of
Substitution.
reaction? So I have a vote for substitution. Do you guys agree?
Yeah.
Yes.
Okay, awesome, because that's correct. And then what is this one?
Addition?
Elimination.
Addition.
An addition reaction. Elimination is when you would form a pi bond. So elimination, you can think of it as getting rid of hydrogen bonds. I personally love doing elimination reactions. They're very fun to draw the curved arrows for. But you guys don't have to worry about that yet. So you guys have things to look forward to in the next couple of weeks. So yeah, so this is substitution and this is addition. So over here, rank the following compounds. Most, also that homework question that you wanted to go over, I feel like it was just a little bit more out of the scope of this exam. It looks like it might be something that will come up on the next exam. So I wouldn't really worry about it right now, so I don't think I'm going to go over it just because I don't want to confuse you guys.
You're talking about the transition state one?
Yeah, the transition state one. I just like don't think that Dr. Dowdy is, I actually know that he's just not going to ask about transition states in that type of detail.
Okay.
So you guys can, he's never going to ask a question like that, to be honest. So I guess that's good news for you guys.
Never know.
I'm like 100% sure. I've taken Dr. Dowdy for Orgo 1 and Orgo 2, and he just like does not ask questions like that. He just doesn't. He might on the next exam. If he does ask about transition states like that, it'll be on the next exam. Yeah, or like on the final or something. But honestly, even then, that's like a long shot. So over here, it's saying for SN1 reactions, does SN1 like primary or tertiary?
Tertiary.
Tertiary.
Yeah, tertiary. And then it'll like secondary after that. So tertiary. And then I think that's like how I would draw the arrow for decreasing. So over here, which one would be the best?
The last one.
Yep.
Yeah,
so
4.
4. And then what do you guys think after that?
Two.
So I have a vote for 2. What do you guys think?
Not 2. I think 2 is just, is it 1?
Is it 1?
Yeah.
Yeah, so it's, yeah.
So this is tertiary, this is primary, this is secondary, and this is secondary. So I guess we're kind of deciding between 1 and 3 here. What do you guys think?
I think
And
it'd be
remember
1
SN1
because the iodine is
Because what?
bigger, so I can get rid of those electrons easier, right?
Yeah, there you go. So I mentioned earlier how the better the leaving group, the faster the reaction. So obviously that means that it's more reactive. And bringing back our little size diagram that we had earlier, we had larger molecules, chlorine, bromine, iodine. Iodine is big, so then after that we would have 1, and then we would have 3, and then lastly we would have 2.
So
Does that make sense to everybody?
Reactions are always going to go like 3, 2, 1.
Yeah, SN1 is always 3, 2, 1. Does that make sense for everybody?
Yeah.
Okay, so I am going to make a question for you guys, and this is going to be a little bit difficult, but let's see, how many people are here? There's 23 people. Okay. Now I'm just going to draw it in. So over here, let's say that we have, actually, no, I'm going to do it like how the question actually is. So it's going to be, Dr. Dowdy loves questions like this, or he likes them in person. So I'm not sure how he would really ask this on an exam, but it's kind of like one of those fill in the blank questions that me and the people in the library at like 2 in the morning used to be like, oh my gosh, I bet he's gonna ask 300 fill in the blank questions, and he would. But it would be literally provide the starting material in the following reaction. And it's like, where do you even start? So obviously this is going to be a substitution reaction since that's what we've been learning. So let's go ahead and like throw up our nice little cyclohexane. That's going to be the same. But what do you guys think is going to be over here?
Sodium?
Would it be like a halogen? But like I don't know how you would decide which one it is.
Halogen. There you go. And we know
Oh,
that
so
we
it can be
denote
any
our
halogen?
halogens by an X. Yes, awesome. And if I were taking the exam in person, I would make like halogen and then bromine, chlorine, like over here fluorine, but not really fluorine. So just those three is what I would write.
Wait, what?
So sodium we know is in the first part of the periodic table. So if you see anything like this that has Na like that, and we know sulfur is in the same row as oxygen. So it also, if it has like those 6 lone pairs, or sorry, 3 lone pairs on it, then it will have a negative charge like that. So that's actually what the atom looks like. Is that cool?
Yeah.
How do we know it would be a halogen? Like what? Why?
Because halogens are leaving groups.
Okay.
Super awesome leaving groups. Okay, so draw the product. So let's say that we have something like this, and then we have a chlorine like this, and this. So is this going to be SN1 or SN2?
I got an A, but my overall grade.
What do you guys think? You're good. SN1 or SN2?
SN1.
My cousin, who's 12, is voting that it's SN1. Are you guys going to disagree with her?
Yeah.
SN1.
Myrna, you're going to disagree with her?
No, I agree with her 110%.
Yeah, so this is going to be an SN1 reaction. So there's a couple of ways that, well, actually, there's literally only one way, because this is a 2 degree. So we have to look at this.
And OH.
Or a nice little solvent here. It has an OH, awesome. So we know that it's going to be able to hydrogen bond. So that means that we are going to do an SN1 reaction. So with an SN1 reaction, what do our products look like? Do we flip configuration or do we get a racemic mixture?
Racemic.
Racemic mixture, awesome. So then we are going to get something that looks like this. And if he has an option that has both, then you put in the option that has both. Cool?
Cool.
Awesome. What does the rate look like for this reaction?
It would be just the, what do they call it? Like the starting one. So like with the CL
Yeah.
and stuff.
Like rate.
Substrates.
Yeah, substrate.
Awesome. Substrate. That is what the rate of the reaction would look like. So let's do another question like this. So am I get your race? You have a question? Okay, what's up?
Yeah, I have a question. Why is it a racemic? I'm confused.
Because it's an SN1 reaction, and we know that SN1 reactions just form racemic mixtures. We can do an SN2 one right now, and I'll show you how that's going to be. Actually, I'm going to erase this top part here. I'm going to get you to erase the top part.
Yeah. Could you remind me what like a racemic reaction is?
So racemic mixture just means that you have both types of enantiomers in the product.
Okay.
And that can be 50-50, it can be 60-30, and this is important when you're going over like when you're trying to like figure out what reaction would be best when making like pharmaceuticals. Like if you're making ibuprofen or something like that, you're not going to want to have a racemic mixture really, because we know that with ibuprofen, there's L-DOPA and D-DOPA, and only one of them is actually active. So you don't want to just be giving people sugar pills. So you're going to want to try and find a way to make the purest compound. And this is kind of like more of an Orgo 2 thing. But honestly, you're never going to have to figure out that. That's like an Orgo 2 lab thing, to be honest.
Are we gonna like the enantiomer I don't know how to say it. The EE with the extra.
Enantiomers. Yeah. Sorry. What about the enantiomers?
It's like enantiomeric excess or something like that, like the EE.
Yeah, you're not gonna have to calculate that, not for this exam. Dr. Dowdy he knows like some people actually don't like math, and it like stresses people out a lot. So he's like super nice. He's just strictly Orgo, super nice guy.
So for this question, like in the two products for the enantiomers, the dash wouldn't turn to a wedge, like the first dash.
So it makes both of these. It makes two products. Racist
Yeah.
mixture. Yep.
So like
now if I were to do, yeah, what's up? If what?
So like on both the products, they both retain the first like dash. Like I'm saying, it wouldn't reverse. The dash wouldn't turn to a wedge. Kind of like how the other one did.
So you just make both products. You make the one with a dash. Oh, this one here?
Yes.
Oh, we leave him alone.
Okay, because it's untouched. Yeah.
He's not. Yeah.
Yeah. Okay.
Untouched. He does his thing.
Okay.
We're only worried about this stereogenic center right there. Cool.
Yeah, okay.
Sorry, it took me so long to understand what the question was. Next one. Do you guys think this is SN1 or SN2?
SN2.
SN2, yeah.
SN2, awesome. So how do you guys know that?
Got a strong nucleophile.
Yeah.
Awesome, strong nucleophile. And then also
secondary.
we have an Aprotic. Yeah, so it's secondary, but both of them do secondary. So that's like a little bit of a tricky like thing that's gonna happen here. So over here, what would happen is that our product looks like this, and is the oxygen with a methyl on it going to be on a wedge or a dash?
Wait, was that a question?
It'd be a dash, right?
Yeah, and it's going to be on a dash. We flip the configuration.
Why is it in a dash though?
Why is it on a dash? Because this is an SN2 reaction. Actually, let me put it in blue.
Doesn't this deal with inversion?
Yep, and SN2 reactions have inversion. I know this is like I feel like when I took the exam, I like didn't understand this concept. I was like so upset that I like hadn't gone over it enough, and I just like kind of like gave up trying to understand this concept. But over here, that top one is not going to form hydrogen bonds. So we know that it's an SN2 reaction. Also, it's an acetone. And Dr. Dowdy mentioned in class, he was talking about how acetone is used to take off nail polish. And I remember sitting in the exam thinking, acetone is used to take off nail polish. And that was the only thing I can remember saying from lecture. I can't remember if it was polar aprotic or protic, or if it was for SN1 or SN2. All I could think about is how acetone is used for taking off nail polish. Anyways, clearly I'm the only person who thinks this is a funny story. So over here, we can just do the top one. We know that it's going to be SN2 based on the solvent. Bottom one is SN1. SN1 reactions form a racement product, which means we're getting two products in our product. And then SN2 reactions have inversion of stereochemistry. So over there, it looks like we would have looks like we would have an S configuration. So then the one on the right is going to be an R configuration. Is everybody good with that?
Yeah, thank you. So for SN2, we would only have one possible product, unlike the SN1 where we had two enantiomers.
Exactly. Okay. And if you guys want to see what the curved arrows look like for these reactions, this is what they look like. So over here we have our O and A like that. Technically our sodium dissociates, so it's just that working on it. Everything is happening in one step for SN2.
Could we also do the arrows for the first one we did?
And over here, we have our dash, we have our wedge, the chlorine on it. Chlorine is going to leave in its own step, giving us this. And then after that, we have our OH is going to come and attack it like this. Yeah, so also something here to mention for SN2 reactions is they do a backside attack, which is why it flips the configuration. And then we have something, I'm gonna erase the rate over here.
Wait, what does that
And then we
exactly mean by backside attack?
It just means that it's attacking the back. So we know that we have if you kind of like imagine the molecule, you can see that it looks like it's not flat because it all happens in one step, but it just attacks from an area where it's free. So it like twists it, if that makes sense.
Yeah, it does. Okay, thank you.
Okay, cool. And then over here, let's just say that we're doing the wedge one, so I don't make you guys confused. When we'd have like that, and this would have like hydrogen on it as well, and then the hydrogen would. This is like technically one step. This getting deprotonated. Then we would have like this in the solution. Again, you guys really don't have to worry about this, but I'm just gonna put it in there anyways.
Are you saying
and you would get plus
the curved arrows? Or what do
sorry, what?
What do we not really need to worry about? The curved arrows?
You don't have to worry about like how that hydrogen is getting deprotonated or what's deprotonating it, I don't think. Like when I went into the exam, I wasn't really too focused on what was deprotonating it.
Okay.
Cool.
But do you think we should know like the curved arrows and like where they go for this?
Yeah, pretty much.
Okay.
I'm going to do one of the questions that you guys, this was an extra credit kind of questions that I had while I was taking this class. So I don't know, maybe he might bring it up as like a real question, but it is something that it's like an evil question, honestly. So do you guys want to do the evil question?
Yes.
Yes.
Do you know if
Okay,
for our exam he's going to have any extra credit questions? Because on our last one,
Can you repeat the question one more time? Sorry.
you know if on any of our exams he's going to have extra credit questions?
Did you guys have an extra credit question on your last exam?
No.
I think that his Alex assignment is like what's counting as his extra credit questions on the exam, because in person he used to do extra credit questions for, at least when I took Orgo 1 he did, and I remember they were like really difficult questions, but he stopped doing it when I was in Orgo 2, and then I think he started doing like extra credit quizzes and Alex assignments, which honestly I think better, because there's like not exam stress while you're trying to figure out the thing that can like save your grade. You know what I mean?
Yeah.
So this is going to be a two-part question. Following reaction. This is probably the last question I'm going to do, and then you guys can feel free to ask me questions if you guys have any. As soon as the video is done processing, which like takes a while, I'm gonna post it on my YouTube channel, which then I will post a link to that inside of the GroupMe. And honestly, it's a disaster video since like the internet went out while I was doing it and everything. Anyways, so over here, do you guys think this is gonna be SN1 or SN2?
Is that wedge in the second part of
It is a wedge, yeah.
Okay.
SN1.
Yeah, SN1.
Yeah, SN1. So you can see that this is going to be, yeah, so technically it's secondary, so it could be either one. But this is Protic. So then our products look like this. OH stays over there. And then we get a race mix product. So then the other one would look like this. And you can keep the OH where the BR was because we know substitution. So you don't really want to complicate trying to like put in the RNS configuration. Honestly, yeah, I would just keep it like this if it were a question. And then part 2 is going to be use the data below. Predict the specific of the product. So over here would be a box, and then one of the products would go in there in a specific rotation for, let's say, this product that has the wedge over there. It's going to be plus or minus 9.9. So specific rotation of P. I'm going to say this one is P. What do you guys think it's going to be? Thoughts?
Would it be positive 9.9?
Yep, it's going to be positive 9.9. Awesome. I'm going to do one more nomenclature question for you guys. Is that fine?
Wait, can I ask you a quick question? Why is it positive 9?
Yeah. Because we're not being asked about what the specific rotation for this is because we changed this BR into an OH. So now we have a different compound. And it's telling us that the specific rotation of this enantiomer is negative 9.9. We know that enantiomers will rotate plane polarized light in the opposite direction. So like, let's say that, I'm actually going to draw a picture to my best ability on like what I'm imagining is happening. So let's say that we have this molecule over here, BR, and you want to shine some light on it. So over here, look, we have like a nice sun. Oh my gosh, that's so pretty. And then it's shining light over here. So then this is going to polarize the light over here. Now, if you were to look at the enantiomer for this, and you have the BR like that, and okay, let's say that light is also going to shine on this one like this. Light is going to be polarized that way. Cool.
Mm-hmm.
So we're not being asked about the original product that is polarizing light in God knows what area. We're being asked about the enantiomer.
I was just confused because
So,
like the image on the square on the left is the same as the one on like the blue square.
so that was the product. So I was kind of just, I drew a blue square so that I could show you that that was the product.
Okay.
I guess maybe I shouldn't have drawn the blue square.
It's okay. Thank you.
Yeah, this is, yeah, and like this is exactly how Dr. Dowdy would word a question. So it's kind of just like understanding how he is asking for it. But also, the good thing about multiple choice questions for the entire thing is that the right answer is in front of you. So if you ever feel like you're taking the exam and you're like totally freaking out while you're taking the exam, kind of just take a deep breath and be like, you know what? Okay, sorry, I just like read one of the questions. Okay, anyways. It's like, you know what? The right answer is right there in front of me. I just have to choose the correct one. So.
But
yeah,
why is
that,
it like one of them's positive 9.9, but the other one's negative? They're the same exact, like molecule.
Yeah, they look the same.
they're not. But are they
Not.
the same molecule?
I think the enantiomer, like each enantiomer is going to be opposite, right?
Mm-hmm.
So
yeah, so like even when we were doing like the super simple questions earlier, like this one when we were looking at plain polarized light, actually since I X'd out the block. When we did this question, let me find it really quick for you guys. Oh yeah, so we did this one. We had NH2. It was telling us that this one is polarizing light in 8.5. It's an enantiomer, which is NH2, same thing, but it was on a wedge, or sorry, on a dash. That was polarizing it in negative 8.5. Same thing. It was just asking a question before that. Does that make sense?
We just make it negative all the time if it's positive.
Yeah, so it just makes it from negative to positive for enantiomers.
Yeah.
Cool?
Yep.
Hopefully that helps. Let's do this one last. Wow. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Are we naming this?
Yeah, you're gonna name it right now. I just drew the wrong compound. Okay, there you go. Name it. Or I can just help you guys name it really quick, and then you guys can have 10 minutes to ask questions. In a second. Cool. Are you guys ready?
Yeah.
Okay, so the answer for this one, let's go ahead and figure out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know that our parent chain is nonane, or whatever. And then, so there's no other substituents besides this here. And we have 2 carbons and then a chloro. So we know that 2 is going to be ethyl. So this is going to be in parentheses like this. And we have 2 chloroethyl. And this is happening at carbon 5. So we have 5 and then in parentheses 2 chloroethyl, because the chlorine is connected to the second carbon of the ethyl. 2 chloroethyl nonane. Any questions about that?
Why did we put it in parentheses?
Why?
Yeah.
Because it's a substituent. So instead of like It's a substituent that has its own carbon chain on it. So that's why you put it in parentheses. So definitely do questions like this because you never know what Dr. Dowdy might throw at you.
Where did the 2 come from? Is it because the chlorine is like coming off of the 2?
Yeah, and you count it moving away from the carbon chain. I wouldn't worry too much just because Dr. Dowdy only has 25 questions to ask you guys. So I don't know if you would waste it on something like this difficult. And I know like 100 English students would email him after the exam saying like, literally, what the hell was that question you just gave us? So.
Exactly.
Yes, if anybody has any questions, I will be here for the next like 10 minutes for you guys. But thank you guys for coming to the review. If you guys want to tell Dr. Dowdy that I'm such a great TA, so you can write me a nice letter of recommendation from med school, that would be awesome. Just like email him, be like, Neda was my favorite TA. She used to fill out the worksheet so nicely. Anyway.
Actually, the worksheets.
We'll do that for you.
Yeah, probably. So yeah, I'll be here in case anybody has any questions. But yes, thank you guys for coming to the review session. I will post it once the video processes. So yeah.
Where do you post your recordings?
I'm gonna post it on my YouTube channel. My YouTube channel is Neda Hamood, so like Neda Neda, Hamood Hamood.
Okay.
Thank you.
Thank you.
Yeah, no problem. Good night, you guys. Like 11 o'clock.
Thank you. Good night.
Yeah, no problem. Good night.
Thank you.
Yeah, no problem. Toodles. Bye.
This is totally irrelevant, but how do you become a TA?
So you get an A in the class and then email him like right after the class and then just be like, hey, Dr. Dowdy. Be like super nice about it too. So, hey, Dr. Dowdy, I'm interested in becoming a TA for you. If that's something that you would allow me to do, I really like your TAs and I would love to be able to help the students as well. And then easy peasy, Dr. Dowdy's always in need of TAs. So yeah.
Awesome. Thank you.
Are we gonna ever
no problem.
find the alpha? Like calculate?
No.
Okay.
That wasn't, that's not something that you guys are gonna have to do. So just don't worry about it.
I was worrying so much about the like math ones, and I feel like none of them are on it.
I'm telling you, like that's one math questions he's gonna ask about that enantiomers and how it like flips the configuration of the plane polar Earth light. So
wait, what?
Yeah.
What do you mean?
This one. That's how he's gonna ask questions. If
Oh.
he mentions numbers, like pretty sure.
So it probably won't have like the bonds formed, bonds breaking one.
No, just
there's the table or whatever.
yeah, it's just gonna be looking at the size of the molecule, and that can be told by the trend that looks like that.
Okay.
Increasing size looks like that.
All right, can I ask you a question? So where do you recommend me getting the like exercises to do from? Because some of the books can be like overwhelming.
Back of the book questions are the best. I would get the solution manual. I think somebody sent the solution manual PDF in the group me one, so you can maybe like text people in the group me and ask them if they found it because it was like sent a while ago. But Dr. Dowdy asks questions very similar to how the book asks questions, so it's the best place to do practice questions. Even sometimes he'll literally like take questions directly from in the chapter and the back of the book. So
Okay.
like yeah.
Okay, keep going.
Sorry, can you repeat that, please?
Oh, so do I do like each end of chapter questions, like chapter 6, and like, does that make sense? I'm trying to say.
yeah, if you have time to do that, I would 100% do like every single question in the back of the book. And the solution manual also has this like part in the beginning where it actually like explains how to do a couple of questions, and then you're able to just like do them on your own.
Okay, great. Thank you.
The solution manual has like a lot
No
of
problem.
questions that we don't really like, that we didn't do it. I don't know how to word it. Like that we probably don't need to worry about. How do you like think we should like should we just kind of focus on the kind that we did today and here, you think?
Focus on the ones that he does in class, and then also the ones that I've done here. But honestly, he can pull any sort of question from the back of the book and it would be fair game. If you were to pull questions from the homework, I feel like the homework is a little bit more in depth than what he goes in with the class. But like back of the book is completely fair game with the like extent of how difficult the material is.
The homework is overcomplicated.
Yeah, I agree. So if you guys don't have any other questions, I think I'm gonna call it a night. I have some biochem homework to do. Yeah, no problem, you guys. Good night. Thanks for coming.
Good night.
Bye.